A very warm welcome to everybody. So thanks to even foreign participants to be present here so early this morning, according to Indian Standard Time. And it's our great pleasure to have Professor K. Raghavan from IMSC to inaugurate this session. And I would like to ask him to say a few words.
Thank you, Amit, very much. First, by way of introducing myself, my name is K.N. Raghavan on the mathematics faculty of Kriya University at the moment. Before moving to Kriya earlier this year, I was for many years, for over 2 decades in fact, part of the mathematics group at Math Science, all variously called Math Science or IMSC, which both forms of which are short for the Institute of Mathematical Sciences in Chennai, India. I am flattered to be asked to say a few words at the beginning of this event. I also feel proud to be speaking, and the reasons underpinning my pride should become clear soon. About this event itself, it is the first of several kinds. The Banff International Research Station, BERS for short, has inked a pact of collaboration with CMI, Chennai Mathematical Institute. Under this collaboration, some of the BERS events will be held in Chennai. The preparation required for a BERS event is elaborate and begins years ahead. The competition for sponsorship by BERS is intense. A proposal by the organizers of the present event has been selected by BERS, and the event itself is scheduled to be held next year in 2025, 29th November to 5th December. Congratulations are therefore due to the organizers of this event. We can all look forward to the BERS event next year. Now, coming to the present event, this is under the ATM schools, that is Advanced Training in Mathematics schools of the NCM, which stands for National Center for Mathematics. This is an AIS, an Advanced Instructional School, under and sponsored by NCM. And it is a precursor to the BERS event next year. This is the first time outside of the pandemic that NCM is sponsoring an event in the online mode. So there were many issues with getting NCM to sponsor the event, many teething issues with the approval process. And I'm happy that all the issues are now ironed out and the event has begun. The organizers, especially Amit and Sachin, deserve our thanks for their patience and clarity of thought during the rather long and tortuous approval process. So much for the organization of this event. Coming now to the academic side of the event, I have known all the speakers, all except the one international speaker, for many, many years. I did a back of the envelope calculation yesterday, and if one adds up all the years that I have known each one of the speakers, the total is well over 100. That many of them have spent some of their impressionable years at Math Science or CMI in Chennai is another thing that I'm immensely proud of. One final word before I finish my few words is that this event is being held online, as I told you, for the first time. And that puts a responsibility on the participants. I request all the participants to follow the online etiquette, which I'm sure Amit and Sachin would have will be prescribing for you from time to time, and make this event a success. Because whether or not we will have the benefit of many more such programs shall depend naturally upon how this one unfolds. Okay, so it only remains for me to wish you all an exciting learning experience of Lie algebras and their representations on the one side and quivers on the other. I look forward as much as you are looking forward to the program. Thank you.
So many thanks, Professor Raghavan. And I should add that without his support, this event would not have been possible. Yeah, that's why he is the guest of honor today. He played a crucial role in us being able to apply for the funding successfully. And once again, many thanks for his few words. And let us now actually go to the first talk of the series. And Sachin, would you like to introduce? Yes, yes, please. You want to say something?
I'll be there for a few minutes, but
Sure.
you will
Sure,
excuse me.
sure.
But I will join. I look forward to joining other lectures.
Okay, sure. Thank you.
So can you hear me?
Yes, yes.
Yeah, so without this thing, so it's my great pleasure to have Shraddha here as our colleague from another IITs. And without further ado, I will request her to start the lectures on the Lie algebras. So please, Shraddha.
Okay, thanks a lot, Sachin. Let me share my slides or from my pad. Oh, right. Okay, so
Shraddha, sorry, just to
yeah.
hold on for a moment. So would you like if people stop you in the middle, or you want somebody to keep track of the chat and then convey questions to you?
I think better if someone can keep track of chat. Maybe Ritesh can do it.
Sure. So
Okay.
I think Ritesh can do that. Thanks.
Yeah,
I will
okay. So, shall I?
Yes,
Yeah.
please start.
So, yeah, so good morning to everyone, and I thank organizers for giving me an opportunity to speak in this AIS, and I'm speaking in AIS first time ever. So thank you to Amit and Sachin both. So the first lecture on Lie algebras will be basically on various definitions, examples, and then we will do some important theorems. I'm closely following these references that you can see on the screen. In past, there have been many AIS on Lie algebras alone. So, for example, in 2011, in math science, which IMSc, which Raghun just introduced, also mentioned in his speech. In 2011, there was a very elaborate AIS on Lie algebras, and interesting thing is that all the lectures are available on Math Science YouTube channel. And also last year there was a AIS partly on Lie algebras again. So and where Apurva has written up some notes up to basically section 5.3 of the main book. And Ritesh will soon share this with all of us. And there are some more YouTube lectures available. For example, when you can look at Uppsala algebra, it has like full course on Lie algebras, and of course. I sincerely request all the participants to browse these references, and please do discuss even this AIS is over. Here is my email ID. You can write to me anytime. Okay, so let me go to the mathematics part now. Okay, so let us first begin with the definition of algebra over a field. So an algebra over a field is a pair A and operation which I'm denoting is star, where A is a vector space over field, and the star is a binary operation on A. That means it's a map from a Cartesian product of A with itself to A, such that this binary operation should be bilinear, where bilinearity means that it should be linear in each variable. There are two slots. In each slot, it should be linear. Okay, so now depending on what kind of more condition we want on this operation, we will have a class of algebras. So for example, if we say that I want my star to be commutative, that means A star B equals to B star A, then one has class of commutative algebras. And if one wants this star to be associative, then one has a class of associative algebras. And Lie algebras are something which are in general neither commutative and definitely not associative. So let me start with an example. So one of the basic example of algebra is that if you look at the vector space of all n by n matrices over a field and look at the usual matrix multiplication, which is a binary operation, and of course it is a bilinear, and with respect to this binary operation, this algebra is actually associative algebra. Okay, and if n is bigger than 1, then strictly bigger than, then it's not commutative. On the same vector space, one has yet another binary operation, which is I'm going to write now. So if you take two matrices n by n matrices and define binary operation a, which I'm writing calling the commutator a comma b, define as AB minus BA, then this is yet another binary operation. And if n is more than 1, strictly bigger than 1, then this one is neither commutative nor associative. This is some nice exercise, one can try it. And but this operation is still satisfied. Binary operation has some other property that it does satisfy. So which I will say later. So let me just now give the definition of a Lie algebra. Okay, so as I said, a Lie algebra is a class of a Lie algebra. So here we will start. Okay, let me show. Yeah, so a Lie algebra L is over a field F is an algebra. So that means I have vector space L over F and a binary operation, which I am going to denote by usually is denoted by this bracket. It's called Lie bracket or just a bracket or commutator. Okay, so and this is a and satisfy certain properties. I mean, certain axioms, which are that if you take the commutator of x with itself, then I should get 0 for all of x, for all x that lies in L. Okay. And further, it satisfies so-called the Jacobi identity. That means if you take three vectors x, y, z in L and look at this commutator uh, in a cyclic way. So if you take the commutator of x with the commutator of y and z, and then you look at the commutator of y with the commutator of z and x, and if you look at the commutator of z with the commutator of x and y, and if you add all three of them, I must get 0. This is called the Jacobi identity. Okay, so it can be easily so on the matrix algebras that we defined this commutator on this vector space. One can check with respect to this commutator AB minus BA. It is actually Mn of the matrix algebra, actually a Lie algebra. And basically, I mean, one has to check this. Sorry about this. One have to check the axiom 1, which is very obvious, and also axiom 2 is also something one can easily check. Okay. So there are some remarks on these axioms. So first of all, since the bracket is a bilinear operation, then using the axiom 1, one has that the commutator of xy and is same as is a minus of the commutator of y comma x. So what does it say? That if if the field of if the characteristic of the field is different from 2, and also assume that the commutator is not identically 0, then the Lie bracket is not commutative, right? So so in general, Lie algebras are not commutative. And further, if Further, if the characteristic of the field is not 2, then having the condition that the commutator of x with x is 0 for all x in L is actually equivalent to saying that this anti-commutativity of the commutators. Basically, just one has to do the bilinearity of the commutator. Okay. So let us do some examples of Lie algebras. So a special class of Lie algebra is called abelian Lie algebra. And so an abelian Lie algebra is you take any vector space and define the commutator to be identically 0 for each pair xy. So it is also called commutative algebra because in this case bracket of xy is same as bracket of yx. So there is a commutativity. And an important class of Lie algebra is called general linear Lie algebras, which we have, in a sense, we have discussed where I was denoting M and F, but let me state it in this manner and fix some notations as well. So suppose V is a vector space over the given field F, then I'm going to denote this GL of V, which consists of all the linear maps on V, all the linear maps. Then one can define, this is definitely a vector space, so one can define a commutator of F and G, where F and G are two linear maps to be F composite G minus G composite F. So if you want to write down in terms of matrices by fixing a basis, this will turn out to be exact the commutator that we have set on the vector space M and F. And this is again it's a routine check to see that this is indeed gives a Lie algebra structure on this vector space GL. And so often if the dimension of V is finite, let's say n, then we can identify the GLV as hello. Your question?
No, I can't see any questions so far. You can go ahead.
Okay. Yeah. So so by fixing a basis of V, we can identify this GLV as n by n matrices over F, and then the commutator that we have defined here for the linear maps transform to this commutator, where A is a matrix for corresponding to F and B is a matrix corresponding to G. By fixing a basis, this is all possible to do. And what follows in several computation in this lecture, we will have to work with certain bases, and a nice basis for the Lie algebra GL and F is can be given by these n by n matrices. So if you take so fix R and S something that lies between 1 and n. So this is n by n matrices where all but R such entries is 0. And this R and S entry R comma Sth entry is equal to 1, the unity element of phi field. Then it's, as we know from our linear algebra, if we collect all of these such matrices, they form a basis for the Lie algebra GL and F. Okay, basis as a vector space. This okay, so the point is that the commutator for these basis elements are very easy to compute because multiplication of these matrices one can explicitly write down. Okay, fine. So let me.
Hello, I have a question.
Yes.
So
Yes.
So by basis of the Lie algebra, do you mean basis of the underlying vector space?
Precisely. That's what. Yes.
Okay. Okay. Fine.
Yeah. So if you want to talk about some, I mean, first you fix a basis and then you compute all the possible commutators. And then it kind of it gives the full structure on your Lie algebra. So that is what we are doing next. So if you do, let me just not show what is written and do it here. So let us compute this commutator of the two basis element here. So by definition, this commutator is I mean, multiplying these two matrices and then multiplying the matrix in the reverse order and then taking the difference. Okay. Now we know how to multiply. This is very easy, right? How to multiply these such kind of matrices. So this is going to be Kronecker delta S P. If S and P are not equal, then this product is 0. If they are equal, then it becomes again matrix of this form RQ, and similarly you can do it for this part, delta QR ES. So where this delta is, or this delta, they are Kronecker deltas. Okay, so before giving more examples, a definition will be useful. Basically, we are going to see a lot of example of Lie algebras which are sitting inside in this general linear Lie algebra, GLNF. So subalgebra of a Lie algebra L is a subspace as a vector subspace, which is also closed under the commutator on L. So that is, if we take for all xy in the subspace M, if you look at all the possible commutators, then that should also be in M. Then we call M to be a subalgebra, or you can also Lie subalgebra sometime to specify. Okay. So, and a subalgebra of general linear Lie algebra is called the linear Lie algebra. And in this lectures, and I think later on also, we are only going to look at linear Lie algebras. We are not going to look at anything other than that. So let us see what are the interesting linear Lie algebras. By linear Lie algebra means subalgebras of the general linear Lie algebra, GLNF, that we have written here. Okay. Okay, so an important class of linear Lie algebras are given by so-called classical Lie algebras. So in the example that we are going to show from 1 up to 4, these are precisely the classical linear Lie algebras. And why? So they will have various names, and why those names are assigned? That is because of they are actually coming from the corresponding Lie groups. We are not going into the detail, but one can look at this exercise 4.9 in the reference 2 and some references more. Of course, we can discuss later as well why those specific names are given in that for these algebras. Okay. So I supposed to not have these things written. Sorry about, yeah. So the first one is called the spatial linear Lie algebra. So this is going to be a subalgebra of the Lie algebra GL plus 1. Okay. So we look at all the matrices in this linear in the general linear Lie algebra whose trace is 0. Okay, so maybe let me just say why it is a subalgebra. So if you take any two matrices A and B, in fact, I don't need to take any two matrices in this vector space SLNF and look at their commutator A and B. So I want to say this again belongs here, right? This is what I have to check, but this is easy because if you look at the trace of the commutator of two matrices is the trace of, just apply the definition of the commutator, so which is AB minus BA, and we know trace is linear, so we can take this out, and we know also again from the linear algebra trace of AB is same as trace of BA, so this becomes 0. So the trace of the in fact the trace of any two commutator of any two matrices is going to be 0, in particular matrices coming from the this vector space. So this becomes a subalgebra of the general linear Lie algebra. It's called the spatial linear Lie algebra, and it is also called the type AL. So when more theory will be developed in Lie algebra course, this type AL, BL, CL, DL is going to come again. So for the time being, you can just think about that type AL means a spatial linear Lie algebra. Okay, so and it's a nice exercise in linear algebra to find a basis for this kind of for this spatial linear Lie algebra. So again, so one can start with the basis, with the given basis that we discussed a while ago for the general linear Lie algebra, and can find a basis for this spatial linear Lie algebra. This is again easy, and then the dimension of the special linear Lie algebra is precisely L plus 1 whole square minus 1. Okay. Okay, so let us now see more example of linear Lie algebra. So now we have to assume that the characteristic of the field is not 2. So a type BL linear Lie algebra is called is same as so-called the odd dimensional orthogonal Lie algebra. So this is again going to be subalgebra of a general linear Lie algebra, but not of odd dimensional because of some reason that I'm not saying. Okay. So first look at this matrix, which is 2L plus 1 cross 2L plus 1, which is it's written in the block form. So here these are actually vectors. This is just one element in the field, and these are vectors, means there are some more zeros written in this form. So this is 12 plus 1 12 cross matrix. So now if we look at all the matrices in the this general linear Lie algebra satisfying the property that SA equals to minus A transpose S, then one can again check that the commutator is preserved. That means if you take two elements here, A and B, then the commutator will also satisfy this condition. This is again is going to be easy. Basically, transpose is linear, and just apply the definition. Okay, so now so it's an exercise that we'll be doing in tutorial to find a basis and dimension of the odd dimensional orthogonal linear Lie algebra. Okay, so similarly one has so-called symplectic Lie algebra, which is called type CL, and again we have to assume that the characteristic is not 2. Right, so if you look at all the so its definition is very much similar like this case. In actually all of this definition is very similar. So if you look at all the matrices again in GL 2LF satisfying this condition, where the matrix S is now 2L cross 2L is with this. Now we have a minus here, and again you can check that it is closed under the commutator, and it's a nice exercise to find a basis and dimension for this symplectic Lie algebra. Okay, so we have one more type, which is called type DL, and it's called the even dimensional orthogonal linear Lie algebras. So again it is defined in the very much as the previous two. So look at all the matrices in GL2LF which satisfy this condition, and where S is given by this 2L cross 2L matrix. So same question, find a basis and dimension. We will do one of these in tutorial. Okay, any question? Okay. So let us move on. So
there is one, Shraddha. So what is the importance of the matrix S in each case?
Yeah, so matrix in each case, as I said, yeah, matrix S is actually coming from some bilinear form. So corresponding to each of these Lie algebras, there is corresponding Lie groups which are defined as which are defined as a groups which are which keep the form invariant, certain bilinear form, and you know the bilinear form can be given from these matrices. So each of these matrices are actually giving bilinear form. So there is a meaning to that, and which I am not going into the detail. Is this okay? Okay, I do not hear.
Yeah, it's okay.
Yeah, it is okay.
Okay, yeah.
Okay. So in fact, in the beginning itself, I've written some exercise, and I mean to look at that and how to obtain from Lie groups to Lie algebra. particularly when exercise is written explicitly. So we can look at that. But the essence of these matrices are actually in the behind there is a bilinear form, and the bilinear form you can give in terms of by prescribing this matrix. Okay. Okay, so there are more linear Lie algebras which are not classical but still of very important in the theory. Basically, if you look at all the start with the general linear Lie algebra GL and F and look at all the upper triangular matrices. So A is here now and upper triangular matrix. And again, if you take the commutator of two upper triangular matrix AB, which is AB minus BA, we know this is if A and B are upper triangular, then AB minus BA will again be upper triangular. So this is a TNF. We are going to write it TNF, and it is again a linear Lie algebra. Similarly, we have so-called instead of looking all the upper triangular, if you look at all the strictly upper triangular matrices, then if you take the commutator of two strictly upper triangular matrix, that is again going to be strictly upper triangular. So this is also become this vector space is also this is also a linearly subalgebra. Okay, so more examples still in the linear Lie algebra, which are important. So yeah. So if you start with the
I have a question.
yeah.
Yeah, so like most of the examples here are based on matrices. So is there a special reason why I mean matrices are important examples of Lie algebras?
Well, yeah, it is. As a theory will develop, you will see the classical Lie algebra. They are going to give some classification thing, and there is some very important theorem due to Ados, which is says that all the Lie algebra or all the finite dimensional Lie algebra or the field of characteristic zero is actually linear Lie algebra. So
Okay,
I mean, we are not going to look at any kind of thing that is not linear. Yeah, thank you. So let us look at Lie algebra of derivations. So if we start with I should have slightly looked at my slides in the morning. All the key points I'm supposed to erase, not to have them at the moment. Okay, sorry about that. So Lie algebra of derivation. So if we have A is an associative algebra, then one can define so-called a derivation, which is a linear map, and will satisfy the product rule as for the differentiation. So what is the product rule for the differentiation? So if you take two elements A and B, since A is algebra, I can talk about their product, then the delta of AB satisfy the product rule that we have for the differentiation. So this is A delta B plus delta A B for all A comma B in A. All right. And if we collect all the derivations on an associative algebra, so basically you're looking all the linear, all the derivations on associative algebra A, then with respect to the usual commutator, this again becomes this becomes a linear, this becomes a Lie subalgebra of the Lie algebra GLA. Okay, so it is an I mean the commutator of two derivation is become a derivation again, but if you do the usual composition, it's not a derivation. So this is again an exercise in the tutorial. So what I'm saying that if you check that this is if you delta 1 and delta 2 are two derivations on an associative algebra A, then delta 1 composite delta 2 minus delta 2 composite delta 1, this is again a derivation. However, if you do just a composition alone, so you can check that if you look at there, it's possible to construct example. If you look at the composition of maps alone, then this is often not a derivation. I mean, one has to avoid this trivial example. So derivation. Okay, so in the context of Lie algebra, there is always a very natural derivation which comes from the commutator itself. So let Lie be a Lie algebra, then we can define, so for all x in L, we can define this map, this is called add x. This is going to be map from L to L, and add of x applied to y in L is going to be a commutator x comma y. And due to Jacobi identity, this is going to be actually a derivation on L. It is just playing the Jacobi identity and using the property of the commutator. So in the context of Lie algebra, there is always a very natural occurring derivation. Okay, so just like whenever we define some new structure on a set, there are various usual notions. One of them we have already seen, the subalgebra. But since we have a multiplication as well, we are going to have a notions on like ideal homomorphisms and all of this, the usual way that we have seen in ring theory on most of the other courses in algebra. All of them make sense here as well. So we are going to have exactly. Let us see the definitions. Okay. So if L1 and L2 are two Lie algebras over a field F, then a linear map from Lie algebra L1 to L2 is called a Lie algebra homomorphism. The definition, as you expected, that it should preserve the commutator. So it's called a Lie algebra homomorphism if phi of the commutator of x comma y is the commutator of the images of x and y via phi. It should be true for all x, y in L1. Right? Okay. So, and some notions, I mean, we are defining some structure, but we want to identify structure only up to isomorphism. So as you guess, the next thing that we can, so when we are going to say two Lie algebras L1 and L2 are isomorphic, if there is a linear isomorphism, which is also Lie algebra homomorphism. So that is why we say two Lie algebras L1 and L2 are isomorphic if there exists an isomorphism between L1 and L2, which is Lie algebra homomorphism as well. Okay, so yeah, so having defined the definition of a Lie algebra homomorphism, we can actually quickly define what is so-called representation of a Lie algebra. And you can also relate it with the definition of a module over a ring. This is exactly same, but with the appropriate wording. So a representation of a Lie algebra L is a pair V and a map P, where V is a vector space, and the map P is a Lie algebra homomorphism from L to general linear Lie algebra GL of V. Then we say V is a question or something. There is some noise.
No, ma'am, no.
Okay. So as I said, this lecture is also fixing a lot of notation and convention. So often we are going to draw phi. We are not going to mention phi very explicitly until required. So we often suppresses phi and simply says that V is a representation of L. So a very important representation of Lie algebra is actually Lie algebra itself become a representation. I mean, it's a representation of itself. It's so-called a joint representation, and this is a very important representation of a Lie algebra. So, so what is it? So I'm going to denote it by the add for the sort of the adjoint, and it's a so here the underlying vector space V is L itself. So Lie algebra L become a representation over itself. So GLL. So here add so X in L goes to add of X, which is a map from L to L again. and add of xy is defined to be commutator x comma y. So why this add is a Lie algebra homomorphism is basically again is due to Jacobi identity. And this is going to be one of the important representation. As you see, you will see many even the structure on so-called semi-simple Lie algebras is obtained via representation, particularly this representation of the Lie algebra. Okay, so yeah, and then some common terminologies. One often says that a representation V of L is also a module over L, and the definition for the module is going to be equivalent to as a definition of representation. But I'll just simply write the definition. So in case someone is seeing for the first time, so it would be good that if you go and check by yourself that these two definitions are actually equivalent. So if V is a vector space over F, and so then we say V is a module over L if we have a bilinear map, which we denote by dot from L cross V to V, satisfying the property that if you look at the commutator x comma y and let it act on a vector V, this would be same as let y act on V and then let x also act on V, and then now you first let x act on V and then let y act on x dot V and take the difference. This should be same for all x, y in L and V in V. Okay, so this is so V saying that V is a module over L is actually equivalent to saying that V is a the representation of L, and this is we often also say that L is acting on V or V has an action of L. So all of these sentences mean the same thing. So they don't have any differences. It's just the equivalent way of saying the same thing. Okay, so now let us define ideals. So just like in the case of ring, a subspace I of almost just like a ring, because we don't have vector space structure on ring. So a subspace I of Lie algebra L is called an ideal of L if for x in L and y in your ideal I, then you look at the commutator x comma y. This must also be in I, and this is sufficient. We don't have to check the commutator y comma x because commutator xy yx is minus of xy. So this is sufficient to write. And every ideal is, you can say, kind of two-sided ideal. We don't have differences as in the case of rings. Okay, so some examples of ideals, like if you take any Lie algebra homomorphism and then look at the kernel of that Lie algebra homomorphism, kernel as defined as a kernel in case of linear algebra, because every Lie algebra homomorphism is also a linear map. So then the kernel phi becomes an ideal of L1. Okay, and some trivial examples, of course, singleton 0 and all of of L. And some other important ideals of Lie algebras are so called the center of L. So it is defined, it is those elements of the Lie algebra X such that their commutator with any element of L should be 0. So x comma y should be 0 for all y in L. So X is kind of commuting with everything. So this also becomes an ideal of the Lie algebra. Okay. And yet another important ideal is so-called the derived algebra of L. So it is denoted by this. Just take the commutator of all the commutators of L with itself, and it's actually span of x comma y such that x is in xy L. Just look at all the commutator x and y and look at their span. And this is again easy to check that it's almost actually from the definition that the derived algebra commutator of L with itself is actually also an ideal of L. So, okay, so what would be the derived algebra of the general linear Lie algebra, GLNF?
So,
why?
Shraddha, so do you need to take F span, like the set of commutators itself is not an algebra, is not a group by itself?
We need we need this, we need the addition as well. First of all, it has to be subspace also, right?
Yeah, so the set of commutators, like the brackets XY, they are not closed under addition.
I mean, they are bilinear. So, like, if we have something like that, something of, I don't know, x1, y1. Yeah, so I'm not, can you always write as a commutator of some same thing like z1, z2? Yeah. So for that, we should better take the F span.
Okay.
Okay, so what is the commutator of GLNF with GLNF? Will someone like to answer from the audience? At least any guess. I mean, if you take the commutator of two matrices in any property, you know that. Sorry?
F is 0, that is SLNF, small SLNF.
Yeah. So basically, if you take two matrices and look at their commutator A comma B, commutator of A comma B is actually 0, no matter what A and B, no condition on A and B are required, right? Because B trace of AB is same as trace of BA. So this says this says that this actually the one side implication that the derived algebra is actually contained inside SLNF. In fact, with some more little bit computation, one can say it's actually equality. So please check it. Okay, it's a nice playing with the matrices. So nothing much is going on. Okay, so whatever the way we have defined the derived algebra, one can actually define for any two ideals the similar notions that if I and j are two ideals of f, then we can define the an ideal which is the commutator I comma j, which is as defined in the case of derived algebra, which is going to f span of the all the possible brackets where x is coming from I and y is coming from j. So this is also an ideal. And the sum of two ideals is an ideal. This is also one can check. Okay. So one more definition. So Lie, because we have already defined an ideal and this definition is totally defined in terms of ideal only. So Lie algebra L is said to be simple if L has no non-trivial, if L has no non-zero proper ideal, and this commutator of L with itself should not be 0. So probably you have this seen the definition of simple groups or simple ring as well. So then you ideals are which corresponds to normal subgroup. So up to here is something that is probably you agree. You may say why this condition is this condition. Soon we are going to define so-called the semi-simple Lie algebras, and we want definition to be compatible with each other. And for that, we better avoid saying that the commutator of L with itself to be 0. Basically, we are avoiding the condition that L should be abelian. We don't say a Lie algebra to be simple if it's abelian. Abelian Lie algebras are never simple by definition. Okay, so what is an example of a simple Lie algebra? So if you look at this L equals to SL2C, which is all 2 by 2 trace less matrices over the field of complex numbers, one can show that it's a computation of commutators, that it has no proper non-zero ideals, and also the commutator is not equal to 0. In fact, in this case, the the commutator of SL2C with itself is going to itself. This is very small Lie algebra. It is just 3-dimensional, and you can explicitly have the basis and do the computation. Okay. So now once we have the ideal, we have naturally notion of quotient, right? So if I is an ideal of L, then the quotient space L mod I, quotient space as a quotient as you do in the vector space, is naturally endowed with the Lie algebra structure. So how do we define the bracket? So the bracket is defined as, so take 2 elements in L mod I, then their bracket is defined to be x plus y, sorry, the bracket of x with y, and look at that quotient. Now, as usual, now whenever we try to define something on quotient, the usual thing to do is to check the well-definedness. That one has to check it, that the above is actually, this is well-defined. That is where you have to use I is actually ideal. And okay, so some more things is, so whenever you have a Lie algebra homomorphism from L1 to L2, then there is a isomorphism, a canonical isomorphism from L1 mod kernel of phi to the image of phi. This is also we have called as first isomorphism theorem, that we have quotient spaces in like group theory, ring theory, and we have in Lie algebra as well. And also more things are true as they are true in Lie algebra, groups and rings. The correspondences of ideals as well. Correspondences. So ideals in the quotient space L mod I are in one-to-one correspondence with the ideals of L. Those ideals of L which contains I. So if you have an ideal J of L containing I, then J mod I becomes an ideal of L mod I. Again, these are all routine check, so I'm skipping the detail. But if you are seeing first time, please ask the questions during tutorial and other time as well. Okay. Okay. So finally, I'm going to move on. Having these notions, I'm going to move on what kind of extra structures one can have on Lie algebras. So in case of groups, we have two notions, so-called soluble, nilpotent. We are going to have here as well. And also one more thing that is going to appear is so-called a semi-simple Lie algebras. And semi-simple Lie algebras, we will have a definition today, but we are not going to say much about it. This is that will be topic for tomorrow. And so let us see what is the definition of nilpotent Lie algebra. So if you remember definition of nilpotent group, then this should look very natural to you. So first we define what is called the descending central series or lower central series of Lie algebra L. It is a sequence of ideals where so I'm just going to write here L0 containing L1 containing L2. So these are all ideals containing Li, and this can go on. And here L0 is my entire Lie algebra L, and L1 is the derived algebra commutator with itself, but L2 is the commutator of L with L1. So L1 is the ideal, L is an ideal, so and commutator of two ideal is ideal, so L2 will be also an ideal, and in general you can define Li to be L commutator of L with Li minus 1. Okay. Then a nilpotent Lie algebra is called nilpotent if for some n this Ln is 0. And another thing, I mean, I have defined these ideals, but you can also check this is contained. There is a descending series of ideals. So we say a Lie algebra is nilpotent if for some n this Ln the term becomes 0, and hence every term after that will also be 0. So this is just going to be a finite series. Okay. So of course, so what are the examples of nilpotent Lie algebras? So any abelian Lie algebra is going to be nilpotent, because in abelian Lie algebra, commutator of any two element is 0. So even L1 itself becomes 0. So it's a nilpotent. Okay, so what is next? The so-called strictly upper triangular matrices, they are also nilpotent Lie algebras. And in fact, these are very kind of the fundamental example of the nilpotent Lie algebra. And soon we are going to see a theorem that why I'm calling it fundamental. Kind of everything is here for the, for the nilpotent Lie algebra. Okay, so here to show that this the Lie algebra of strictly upper triangular matrices is nilpotent Lie algebra, one has to play with this kind of commutator, and here working with the basis of this, finding a nice basis for this, and then finding the commutator, that is what is going to work out. In tutorial we are going to solve this one. Okay, and but what is not an example of is every Lie algebra nilpotent? Of course, the answer is no. So if you look at the upper triangular matrices where assume that n is to be strictly bigger than 1 to avoid the trivialities, then it is not going to be nilpotent. So one can just play with the commutator here. So if you compute the commutator of the derived algebra of the upper triangular matrices with itself, you get the nilpotent ones. Fine. Okay, so then we compute the next one. So if you compute the derived, if you compute the commutator of the entire Lie algebra with the derived one, which is the nilpotent one, then we get back again this one. So it stabilizes. So if your n is strictly bigger than 1, then this is not going to be 0. So this is not upper triangular matrix. Of course, this is a very sketchy. I'm just writing the key points, and the tutorial we are going to have the details about. This is basically some computation with basis of TNF. Okay. Okay, so now some properties about nilpotent Lie algebras. So again, these are going to look you natural if you remember some properties of the nilpotent groups from group theory. So if subalgebras and homomorphic image of nilpotent Lie algebras are nilpotent, and proof are again actually routine. So I'm going to skip it. And if the center of L, we know we have defined the center of L of an ideal of a Lie algebra, and center of L is an ideal. And if the quotient Lie algebra L mod center of L becomes a nilpotent, then it says that the L is also nilpotent. And it's a property of Lie algebra. If it's a nilpotent Lie algebra, that if L is non-zero nilpotent, then the center of L is actually non-trivial. So this helps in, for example, this kind of thing helps sometime to say something to, if you want to know something is nilpotent or no, you can look at its center, and if it becomes 0, then it is definitely not nilpotent. So these are important properties of nilpotent Lie algebras. Okay, so the definition of nilpotent Lie algebra actually can be rephrased, and it is going to then pose an important question, which is a theorem of Engel. So okay, so if the the definition of nilpotent Lie algebra says that there exists some n such that this commutator commutator Ln, such that the Ln, which is the commutator of L with Ln minus 1, should be 0. And this is equivalent to saying that if you look at the this recall add is a map from L to L, add x is a map from L to L, and if you compose all possible add up to n many of them and apply to any element of y, this must be 0. This is just actually coming from how you define the add. Add is defined in terms of commutator. So you iterate it and it should be 0. Now this is for all x1, for all x1, x2, xn in L, and for all y in L. Now, if you specialize x1, x2, xn to some elements, suppose all of them are equal. This is quite possible. This is because this is for all elements in L. So you can also assume that when they are equal, then you get add x to the n is applied to y is 0 for all y in L. Okay, and this precisely says that this map add x is from L to L is actually nilpotent for all x in L. So this is a consequence. If your Lie algebra L is nilpotent, then add x, which is a map from L to L, is actually nilpotent for all elements of your nilpotent Lie algebra, right? So what about the converse? What about the converse? So this is the the converse is actually a theorem due to Engel. So converse means like suppose I know that suppose add x is nilpotent endomorphism. If sorry, I don't know if that is causing confusion. Nilpotent endomorphism as we define in linear algebra, right? It's just that. Okay, so suppose add x is nilpotent endomorphism for all x in L, then does it imply L is nilpotent? Nilpotent Lie algebra. So answer to this one is true, and it's actually a theorem due to Engel. So if all elements of L are add nilpotent, means add x is nilpotent for each x, then the Lie algebra itself is nilpotent. So okay, so I'm not going to prove it, but saying some key steps, and actually one of the key step that proves this theorem has more important consequences that we are going to address. So yeah, so now this is we are going to, the point is that look at the adjoint representation. So how I am going to relate arbitrary L to something something related to L? The best thing is to look at the adjoint representation of L, which is there for any Lie algebra. So add is a Lie algebra map from L to GL of L. Okay, and this is easy thing to check that the kernel of this add is actually center of L, and then L mod center of L is isomorphic to image, which is add of L, and this add L is actually subalgebra of general linear Lie algebra GLL, just by from the definition. So if somehow I can show that this add L becomes nilpotent, then then one of the properties for the nilpotent Lie algebra, I can conclude that L is also nilpotent. So, but before that, one has to so how I mean, one has to have some way to say some way to analyze the nilpotent endomorphisms in the general linear Lie algebras. So this is a very important theorem. So if L is a Lie subalgebra of GLV, general linear Lie algebra, consisting of nilpotent endomorphisms, I'm not saying L is a nilpotent Lie algebra. In fact, then this conclusion need not be true. So saying that L is a some subalgebra which consists of nilpotent endomorphism, then there exists a non-zero vector says that L acting on V naught is equals to 0. So all it is saying that this vector V naught is actually common eigenvector for all the endomorphisms in L. So this theorem in a very specific case, when the dimension of the Lie algebra L is 1, is actually trivial, because we know that dimension of L is 1, then L is basically your some span of some single some map F from V to V, right? And F is nilpotent, and F is a nilpotent endomorphism. So F is nilpotent endomorphism. Then we know in linear algebra from nilpotent endomorphism always has an eigenvector. So this theorem in dimension of L equals to 1 is actually linear algebra. Okay, so in general, is also true. I mean, if it consists of nilpotent endomorphism, then it has a common eigenvector. Again, I am going to skip the proof. But let us write down some consequence of this theorem, which says that under the hypothesis of this theorem that when L is a subalgebra, Lie subalgebra of the general linear algebra consisting of nilpotent endomorphism, then I can actually embed inside the Lie algebras of the strictly upper triangular matrices, which are nilpotent. So, okay, so let us see, assuming this theorem, let us see the proof of this corollary. So, okay, so the hypotheses are same as in this theorem stated. So, so L is a Lie subalgebra consisting of nilpotent endomorphism. So, from the theorem, so from previous theorem. So, we have a vector, a non-zero vector, says that L dot V0 is 0, right? So let me take my let me write that actually V1. I don't confuse. Just let V1 and okay. So if you look at the quotient vector space V mod V1, I mean just which is a span of V1. Then this is also L module. I mean, on V mod span of V1 or on this vector's quotient space also L acts, right? And it is again going to act by nilpotent endomorphisms, right? And L acts on V mod span of V1 by nilpotent endomorphisms. Okay. So then we can use actually induction on this dimension of V to say that okay, so here I should say what is n. So here this n is actually dimension of V. So there exists some basis. So basis like I am going to write V2 plus span of V1 dot Vn plus span of Vn. So basis of V mod span of V1 such that the matrix of any endomorphism in L is going to be an strictly upper triangular matrix. So now, so we have a basis for V mod span of V1. So if we attach, if you look at the vector V2 Vn and attach V1 to it and write matrices, and then so let B equals to this, then matrices of any endomorphism in L with respect to B is going to be strictly upper triangular. So any Lie subalgebra of GLV which consists of linear nilpotent endomorphism is actually can be embedded inside the strictly upper triangular nilpotent Lie algebra. Okay, so here is some exercise to think. So is every nilpotent Lie algebra GLVs contained inside this? So I think we'll take this in tutorial, but you can think about it. Okay, what is the guess? Maybe you can is are we saying that every nilpotent Lie subalgebra of GLV is contained inside NNR? I mean, can we conclude whatever we have discussed so far about nilpotent Lie algebra? Can we conclude anything about this one? This exercise? Any guesses? Right or wrong is not a problem.
No in general, but up to a choice of basis, yes.
No, that is a point I want to emphasize. The point is, in the Engel's theorem, the importance is that it should consist of nilpotent endomorphism. Then we have some conclusion. It's not saying that every nilpotent Lie algebra is contained inside here. Okay, even what you're saying, choose choice of basis. So you can just think about, if you take your L to be the span of the identity map, right? Identity map is not nilpotent endomorphism, but L is nilpotent, right? Being abelian, right? So this is one dimensional. This is actually abelian. So L is abelian and so nilpotent. But we can never embed inside, no matter what basis you choose. The matrix of the identity matrix is going to be the identity matrix. So you can never embed inside it. So a common confusion about Engel's theorem is that we often overlook the hypothesis is actually says that it's consisting of nilpotent endomorphism. It is not saying L is a nilpotent. It does not start with L is nilpotent Lie algebra, which is stronger than saying that. Not stronger, weaker. I don't know. I'm sorry. The whole point is that focus on this. This is important. This is important. The hypothesis does not say nilpotent Lie algebra. It says that consisting of nilpotent endomorphism, then I can embed inside. But if you start with nilpotent Lie algebra, then it's not guaranteed that you can embed inside it. Never sit inside. Okay, fine. So now I will move on solvable Lie algebras. We have similar theory as in case of nilpotent Lie algebras. So a derived series of L, a Lie algebra L, is the following sequence of ideals. So again, you start with L0, just to L1, L2, so Li. So here again, your L0 is entire Lie algebra L, and L1 is the commutator of L with itself, which is the derived algebra, and then L2 is actually the commutator of L1 with itself, and you continue. So there is a slight difference. There's not slight, in fact, there's a difference between the derived series and lower center series, so one should not confuse. Li minus 1, Li minus 1. And a Lie algebra L is said to be solvable if this L to the n bracket n should be 0 for some n. Okay, so what is the relation between nilpotent and solvable Lie algebra? We have since every nilpotent since whatever we have defined, this Ln is actually always contains Ln. The reason is that, I mean, here we are looking commutator with the smaller thing, right? After the from the second step onwards, we are looking the commutator with the smaller things. Each step, this one is actually getting it's not same as in the lower center series. In lower center series, it was always entire L. So the L to the n is actually always contains L to the bracket n. So if the Lie algebra is nilpotent, it is going to be solvable as well. So if this becomes 0, then obviously this also becomes 0. That's it. And the non-example of nilpotent Lie algebra, which was all the upper triangular matrices, n by n matrices, which we said is not going to be nilpotent, it actually becomes solvable. It is actually solvable. This is again we are going to look at in tutorial. again playing with the commutator of basis elements, and being upper triangular matrix, finding the basis is also very easy. So what is a non-example? So non-example, one can see, one can have this SL2C. So if you look at, again, the main thing is that, I think I said it some time ago, if you look at the commutator of SL2C with itself, you get back the entire SL2C. So it is never going to become zero. SL2C, the three-dimensional Lie algebra, of course, is not zero. So the derived series, in the derived series, no term can ever be zero. So this is SL2C is not a soluble Lie algebra. Okay, so as usual, we are going to have some properties for soluble Lie algebras again. So subalgebras and homomorphic images of soluble Lie algebras soluble. And if I is a soluble ideal of I, then the quotient is also solvable. This is actually sorry. If I is soluble, then L mod I is of course soluble, because homomorphic image of soluble is soluble. The second one saying that if I is soluble ideal of L and L mod I is soluble, then L itself becomes solvable. Something useful. And the next one is actually is very important, because it's going to give us some very important definition which allows to work more. So if I and J are soluble ideals of L, then so is I plus J. Then basically saying that sum of two soluble ideal is always solvable. So in the I did not state this isomorphism thing, but you have seen similar results in the ring theory, definitely. So if you look at I plus J, ideal I plus J, which contains J, so I can talk about the quotient I plus J. And this is actually turns out to be isomorphic to I quotient of I mod I intersection J. So this is using this we can easily see that I plus J will always be soluble. Let us see why. So since I is soluble, so I is given to be soluble. So I mod I intersection J is soluble. Quotient of soluble is soluble. Okay. So from this isomorphism, using this isomorphism, this implies that I plus J mod J is soluble. Okay. Now in the hypothesis, it is also given to be the J is also soluble. So as J is also soluble, so you can imply B to say that I plus J is soluble. So you have quotient is soluble, and the ideal you're quotienting out, that is also soluble. So the entire thing is soluble. And this is very important property of soluble. So let us write down what is the consequence. So if we start with a finite dimensional Lie algebra, then what we can say that L always contains a unique maximal soluble ideal. Why? So of course, the zero ideal is soluble. So with respect to, so maximality is with respect to containment. So with respect to containment, okay. So we can start if we can definitely locate a maximal ideal, and if you have more than two maximal ideals, then you can add them. That will if you have more than two maximal soluble, you add them. That is again going to be a solvable, right? So if they were so that will imply one is actually contained in another because of use the maximality. So that is why we are going to have a unique maximal soluble. Being finite dimensional, locating a maximal is not a big deal. The big deal is the property here is that the uniqueness. We are actually going to have the unique maximal soluble ideal. And the idea is basically start being a finite dimensional, you can have a maximal ideal, and that has to be unique, because if there was something else, you add them, that will become a solvable. And then that is going to give some contradiction with respect to containment if they were not equal. Okay, so then this gives a very important definition. if L is a finite dimensional Lie algebra, then it has a unique maximal soluble ideal, just like we have observed. So this, the unique maximal soluble ideal is called the radical of L. Maximal soluble ideal of L is called the radical of L. And we are going to just denote it by rad L. Okay, so a Lie algebra is called semi-simple if its radical is 0.
Shraddha, there is a question.
Yes.
Is the hypothesis of B for all solvable ideals I?
Meaning, if I is soluble ideal of L such that L mod I is soluble, then no, as long as you find one soluble ideal such that L mod I is soluble, then L will become soluble. It's not saying if for all soluble ideals such that L mod I is soluble. I think if I understood the question correctly.
Yeah, I think Shubhradeep said, yeah, okay, yeah.
Okay, perfect. Okay. Yeah, so oh, what happened? Hello? Hello?
Yeah, you are there.
Okay, suddenly that screen has disappeared on my laptop, so I thought I'm out of the, okay, sorry.
No,
Okay,
no, you
good.
are in the meeting.
Perfect, perfect. Yeah, so I'm not going to say much today on semi-simple Lie algebras, but the definition, the definition of semi-simple Lie algebra comes by looking at so-called soluble ideals, basically saying that it has no non-zero proper soluble ideals. Sorry. Yeah. So, but I'm not going to say much about semi-simple Lie algebra today. That is a topic for tomorrow. But some simple things from the correspondence of ideals of the quotient, you can say that actually L mod radical of L is actually ideal by definition. So L mod radical becomes always a semi-simple, no matter what your Lie algebra was. Okay, so now let us come to analogous important theorem for the soluble ideal similar thing that we have seen for the nilpotent Lie algebras is this. So here we need to put some condition on the field. So we need to assume that field is algebraically closed, and also we need to assume that the characteristic of F to be 0. So it says that if you have a soluble subalgebra, now there is a slight, it's not exactly the, same statement just by replacing nilpotent by soluble. First of all, we don't know the meaning of soluble endomorphism. So one has to have the statement properly. So just we are not simply replacing soluble by nilpotent. So if L is a soluble subalgebra of the general linear Lie algebra and dimension of V is finite, and suppose V is a non-zero vector space, then V contains a common eigenvector for all the endomorphisms on L, right? So this statement is again going to be obvious if the dimension of L is 1, right? So if the dimension of L is 1, then what? Then your L is basically span of some single endomorphism F. And now that is where we need that F to be algebraically closed. So if your F is algebraically closed, then you know that every endomorphism is on your finite dimensional vector space has an eigenvector. So this statement is obvious if the dimension of L is 1. Now looking at the time, I'm not going to say, let me first complete some consequences of this theorem, and then we can see how much time we have to see the theorem, to see a proof of this theorem. I have written some steps, but let me go ahead to the consequence. Okay, so now if L is a soluble subalgebra of general linear Lie algebra, basically same hypothesis as in the theorem that we have seen, then we can say that there exists a basis of V such that the matrices of all elements of L with respect to that basis is actually going to lie in this upper triangular Lie algebra of upper triangular matrices. So here you can just actually say that every soluble is it's actually by choosing a basis you can embed inside, because the theorem hypothesis is different. It's not exactly same for Engel's. I mean, I'm just trying to emphasize that's a very common confusion for the Engel's theorem. So okay, so if you know the if you assume the theorem that every soluble subalgebra of GLV has a common eigenvector in V, then this is actually same proof as we did for the corollary in the nilpotent case. So same proof. So how we are going to start is first we have to locate a vector. So so we can have a there exists a V1 in non-zero vector such that x dot V1 is some scalar, which I'm going to write lambda of x to emphasize its dependency on the vector x, on the element x V1 for all x in L. Sorry, yeah, x in L, and lambda of x is in your scalar. Now you know how to do it. You can just do the same thing. So look at the V mod span of V1. Right? And now then you can choose a basis such that the matrices are going to lie in the upper triangular ones, and you just in that basis you then you just adjoin this vector V1. That will give a basis for the entire vector space V, with respect to which every element of the soluble Lie algebra is going to be upper triangular matrix. So basically, upper triangular matrices give the most fundamental example for the soluble Lie algebra. Okay, so let us see some consequences of this corollary. Let me add some page. Since giving a proof, I do not have time to give a proof for that, but I can say about this exercise, which is useful to state some, motivate some statement. So if L is a soluble subalgebra of GLV, you assume all the hypotheses on your field that characteristic of F is 0 and F is algebraically closed. So very much you can just work with F equals to C, complex numbers. Then it gives some kind of trace condition. Then it says that the trace of x comma y must be 0, where x is coming from the derived algebra and y is anything. Y is any element of L. So why is it true is that so x is coming from the derived algebra. So what can we say? So how does it going to look like? We can say something using this theorem, the corollary. So using the previous corollary, we can find a basis of V such that matrices in L are basically upper triangle, right? So now we can do matrix multiplication to obtain this result. So I can think of X is my some upper triangular matrix. There's something here and here, and Y the same thing. But look, my X is coming from the commutator, right? So X pretty much I can trace is something linear. So I can actually pretty much just think that X is something like Z1, Z2. Without loss of generality, I can think about that. And Z1, Z2 are in L, right? So for Z1, Z2 also we have upper triangular matrices, right? Sorry. Z1, Z2, they are also in L. I can also write them as upper triangular matrices. What can you say about the commutator of Z1, Z2 then? How, I mean, is it, of course, it is going to be going to look like upper triangular, but is it something more that you can see? So first of all, what is the commutator of Z1 and Z2? By definition, it is Z1, Z2 minus Z2, Z1. So how does it look like? Any response? from audience. This is matrix multiplication. Of course, I mean, okay, let me say, can you say something about the diagonal entries for the commutator?
Will it be strictly upper triangular?
Yes, it is going to be 0 because when you multiply the upper triangular matrices, the diagonal entries they simply multiply with each other, right? There's no linear sum. There's just a linear combination. It just multiplies. So the diagonal entries for Z1, Z2 and Z2, Z1, they are same. So when you subtract, so here you get always 0. Fine, right? So now when you multiply X with Y, what do you get? Y is any upper triangular and X is strictly upper triangular. So when you multiply X with Y, the same reasoning, in the diagonal you are going to get 0. And what is trace of XY? 0. So this basically gives the so using the Lee's theorem that if L is a solvable Lie algebra, then one can say that trace of xy is 0 for all x that lies in the commutator and for all y in L. So what about the converse? So there is some trace condition when we using solvability. There is some trace condition, right? This must be true. If the Lie algebra L is solvable, this must be true. So what about the converse? And so the converse is actually true as long as your characteristic of field is 0, and it is called Cartan's criteria. So Cartan's criteria for solvability is that if L is a subalgebra of GLV, dimension of V is finite. Suppose that trace of xy is 0 for all x that lies in the commutator and y in L, then L is solvable. So this is about the general linear Lie subalgebra. You can also by looking at adjoint representation, you can also write it for the general Lie algebra. So if L be a Lie algebra, of course finite dimensional. So let L be a finite dimensional Lie algebra such that trace of add x at y is 0 for all x in the commutator of L and y in L, then one can say L is solvable. So to get this corollary from Cartan's criteria for solubility, you look at this map add from L to GLL. Then of course, then what subalgebra you have to look at? So if you then add of L, basically image of Lie algebra L under this adjoint representation, this is a subalgebra of GLL. And this condition which is written here is precisely translated to the condition here. So from here you get that add of L is solvable. Okay. So using your first isomorphism theorem and noting that the kernel of adjoint representation is the kernel, is the center of L. So L mod center of L is isomorphic to this. So from here we have L mod center of L is solvable. And center of being abelian, as center of L is abelian, so solvable. So combining all of this implies that L is solvable. Okay, so I am going to, I cannot definitely complete the theorem of this proof, proof of this theorem in 2 minutes. I'm going to skip it. We can discuss during tutorial or some other time. They said you can also write an email or anytime we can find some way to discuss. I think I should stop now. If you have any question, please ask.
Thank you, Shraddha. So there is one question by Sadanand. He said we should take it only after the session is over. That if L is a Lie algebra spanned by the identity, so if is one-dimensional and abelian, should it be mapping identity to the elementary matrix E1n? Actually embeds L into NNF. Nevertheless, the stressing about the nilpotent endomorphisms is something I do get, but I don't get why abelian Lie algebras cannot act as nilpotent endomorphisms?
No, the question was it is contained inside. I mean, I think he's saying that saying that add of identity of
Sadanand, I
B
think you
is,
can speak. That's better if you are around.
Yeah, so I was thinking, I understand why the stress about the nilpotent endomorphism, acting as a nilpotent endomorphism. I thought just mapping identity to E1n, the top right corner.
identity where you are mapping. I mean, what you're trying to give us some isomorphism or some embedding of.
Yeah, L2n
So what is your map?
identity
Goes to?
to E1n, elementary matrix 1, n.
Okay. But this is not embedding. I mean, let me just E1n. Okay, you can somewhere just put one here. So is it a Lie algebra?
Yeah, so that's an abelian sub of n. So it's one dimensional and it's going to be an embedding, right? I mean, I do
No,
get
but
your.
my question was, can you find a basis so that you can actually write it inside inside this nilpotent? That was a question.
Oh,
I mean,
okay.
I'm not saying it is embedded inside.
Okay, then I
You have
understand
to, I
you.
mean, check the commutator Lie algebra moves. Yeah.
Okay. Okay, thank you.